It all began with a launch, the moment a fragile machine with incredible precision set out on a journey no one had ever attempted before. Voyager 2 was not just any spacecraft. It was humanity's first envoy to the outer planets, a silent observer tasked with uncovering the secrets of worlds we could barely imagine. Its trajectory took it past gas giants and icy moons, revealing environments that seemed practically alien in their strangeness. The data sent back to Earth forever changed our understanding of these distant worlds. Voyager revealed Jupiter's raging storms, Saturn's intricate rings, and Neptune's supersonic winds. But it was a brief encounter with Uranus, the least studied of the giants, that left us with the most enigmatic mysteries. Secrets hidden in the planet's magnetic field, its moons, and its strange lopsided tilt. Voyager's journey may have concluded decades ago, but its discoveries still resonate with the questions we ask today. By revisiting its data with modern technology and fresh perspectives, we are uncovering things about these worlds, particularly Uranus, that Voyager itself could never have imagined. The flyby over Uranus performed by NASA's Voyager 2 spacecraft in 1986 was a milestone in our exploration of the outer solar system. For the first time, we had the chance to closely observe this distant, mysterious planet. Its blue-green hue, faint rings, and tilt so unique that Uranus rotates around the sun like a rolling ball. However, beneath the stunning images and data gathered during this encounter are findings that suggest the understanding we gained from Voyager's observations, particularly of its magnetosphere, may need to be revisited. The journey of Voyager 2 to Uranus occurred under atypical conditions. The spacecraft arrived just days after a rare and intense burst of solar wind, a high-energy surge of charged particles from the sun that compressed the planet's magnetic field to a fraction of its normal size. Solar wind, a constant stream of charged particles from the sun, usually shapes planetary magnetic environments, creating magnetospheres that shield worlds from harmful solar radiation. In this case, the solar wind's intensity was so high that it compressed Uranus's magnetosphere to about 20% of its usual volume, significantly skewing the data the spacecraft could collect. According to a recent study published in Nature Astronomy, such circumstances are rare, occurring only about 4% of the time. Had Voyager arrived a week earlier, it would have observed a much larger magnetosphere, more in line with those of other giant planets like Jupiter, Saturn, and Neptune. Previously, scientists believed that Uranus's magnetosphere was unusually weak, with low plasma concentration and highly energetic radiation belts. Plasma, a state of matter where atoms split into charged particles, is a common feature of other planets' magnetospheres, particularly those with strong magnetic fields. Voyager's data suggested that Uranus's magnetosphere lacked plasma from the solar wind and its moons, leaving its plasma environment abnormally sparse. However, new analysis points to a different conclusion. The solar wind likely suppressed plasma presence in the planet's magnetosphere, leading to the mistaken belief that Uranus was devoid of significant plasma. By reassessing the data in light of the solar wind's unusual intensity, scientists have uncovered an error in interpretation. They now believe that Uranus's magnetosphere is more akin to those of other giant planets than previously thought. Additionally, this research has changed our understanding of Uranus's moons, Titania and Oberon. Previous Voyager observations indicated that these moons orbit outside the planet's magnetosphere. Researchers now suggest these moons are likely within the protective bubble of the magnetosphere, which could have significant implications for understanding the potential subsurface oceans on these moons, a growing area of interest as scientists continue to explore the possibility of life in the outer solar system. When charged particles from solar wind interact with a planet's magnetic field, they exert pressure that can compress, expand, or even reshape the magnetosphere. This interaction is not static. The conditions of the solar wind are constantly changing under the influence of factors like solar activity and the planet's distance from the sun. On planets with strong magnetic fields, such as Earth, Jupiter, and Saturn, the solar wind can significantly influence their magnetospheres, creating protective shields that guard the planet from harmful radiation. The magnetosphere is essentially a planet's defense system, shaped by its internal magnetic field. It acts as a shield, deflecting and redirecting charged particles. However, the system is not impervious. The strength and size of the magnetosphere depend largely on the dynamic pressure of the solar wind, which varies in intensity and velocity. At the time when Voyager 2 completed a flyby of Uranus in 1986, conditions were extreme, as the dynamic pressure of the solar wind was at its peak. The dynamic pressure of the solar wind is the product of the solar wind's mass density and the square of its velocity. Under normal conditions, Uranus's magnetosphere extends about 22 to 25 planetary radii from the planet. However, during the flyby, the magnetopause, the boundary where solar wind pressure balances the planet's magnetic pressure, was compressed to 17.3 Uranian radii. As solar wind pressure increased in the days leading up to the flyby, the size of the magnetosphere decreased significantly. This compression not only affected the magnetopause, but also likely influenced the unusual behavior of the planet's radiation belts. Typically, radiation belts around planets are formed from plasma sourced from the planet's atmosphere, moons, and the solar wind. The intense solar wind during Voyager's approach likely pushed plasma out of Uranus's magnetosphere, leaving the region depleted and altering the typical behavior of its radiation belts. As a result, an unexpectedly intense belt of electron radiation appeared, puzzling scientists for decades until new findings emerged in October of this year. The unique nature of Uranus revealed during Voyager 2's flyby has long puzzled scientists. The spacecraft data indicated an unusually tilted and offset magnetic field, contributing to the perception of Uranus's magnetosphere as extreme and unlike any other in the solar system. However, studies have shown that this interpretation does not fully reflect the true dynamics. Compressing magnetospheres, like what was observed at Uranus, are not static changes. They initiate a cascade of dynamic processes. The increase in solar wind dynamic pressure led to the injection of hot plasma from the magnetotail into the inner magnetosphere. This process is similar to what's been observed on other planets, such as Saturn, where solar wind compression events amplify kilometric radiation and cause magnetic field reconfigurations. For Uranus, the result was a more intense electron radiation belt and changes in the plasma composition of its magnetosphere. Interestingly, the intense solar wind conditions likely caused Uranus's magnetosphere to behave similarly to those of other giant planets like Jupiter and Saturn. As the magnetosphere compressed, the radiation belts may have become more charged, similar to what occurs during geomagnetic storms on Earth. This phenomenon is well documented on Saturn, where magnetospheric compression increases electron radiation. On Uranus, an event like that could have intensified electron flux in the radiation belts, even though the planet's environment was previously thought to be nearly devoid of plasma. Increased radiation during this compression event may have also triggered changes in the magnetotail dynamics, such as magnetic reconnection. This well-known process, observed on planets like Earth and Saturn, could have ejected plasma from the magnetotail into the inner magnetosphere, further altering plasma density and radiation levels. For instance, similar events on Saturn have been linked to enhanced radiation belts and intensified auroral emissions. However, the dynamics of Uranus's magnetosphere under these extreme solar wind conditions were not entirely predictable. While we have a fair amount of data about how magnetospheres behave under compression on other planets, Uranus's highly tilted axis and skewed magnetic field complicate these interactions. Uranus's tilt may create unique magnetospheric configurations, potentially contributing to the observed intensification of electron flux and the unusual behavior of its radiation belts. Now that scientists have revisited the dynamics of Uranus's magnetosphere, understanding how these conditions affect the possibility of subsurface oceans on the planet's moons has become crucial. The outer moons of Uranus, namely Titania and Oberon, have always intrigued researchers, especially regarding the potential existence of subsurface oceans. These moons orbit Uranus at distances of 17 and 22.8 Uranian radii, respectively, placing them in a unique position relative to the planet's magnetosphere. For the moons located within the magnetosphere, such as Miranda, Ariel, and Umbriel, any subsurface oceans are more likely to be detected through magnetic induction, as the planet's magnetic field would generate currents in the moon's conductive layers, producing measurable responses. However, Titania and Oberon present a different challenge. Positioned near or just beyond the magnetopause, the boundary between Uranus's magnetic influence and the surrounding solar wind, these moons are less likely to experience the same level of magnetic interaction. Earlier studies suggested that Titania and Oberon might remain outside the magnetosphere for significant portions of their orbits. This would hinder the detection of any subsurface oceans, as these moons would be exposed to the solar wind and the magnetosheath, a turbulent region between the magnetosphere, making magnetic induction measurements practically impossible. However, new data indicates that Titania and Oberon likely remain within the magnetosphere for most of their orbits. According to simulations, Titania has less than a 4% chance of crossing the magnetopause, while Oberon's probability is slightly higher, at about 13%. This means that, contrary to previous assumptions, these moons are generally located within Uranus's protective magnetic bubble. This finding significantly impacts our detection of subsurface oceans, as the moons remain under the protection of the magnetosphere for most of their orbits. The potential for magnetic induction becomes much more feasible than previously thought, opening new avenues for exploration. This conclusion also holds important implications for plasma interactions between the moons and the planet's magnetosphere. While the magnetosheath is typically a plasma environment dominated by the solar wind, the moon's orbits within the magnetosphere mean they interact primarily with magnetospheric plasma. This interaction is likely to be far less disruptive to magnetic induction measurements, making it easier for future missions to detect any subsurface oceans. Science is never static. It is a constant process of discovery, refinement, and sometimes correction. The case of Uranus demonstrates how new data can challenge old assumptions, prompting us to rethink what we thought we knew. However, to truly understand this distant planet, we must revisit it with new technologies. A future orbital mission could provide continuous high-resolution data to study the planet, its moons, and its rings in greater detail. As preparations for future missions to the Uranian system progress, new insights into the positions of Titania and Oberon within the magnetosphere are critical. Besides, understanding the dynamics of the solar wind and the variability of the magnetosphere will influence flight trajectories, ensuring spacecraft arrive at optimal times for data collection. Magnetic induction studies, which have proven successful for other icy moons like Europa and Enceladus, can now be applied with greater confidence to Titania and Oberon. A mission specifically targeting these moons could employ magnetic sensors to investigate their internal structures for signs of liquid water presence beneath their icy shells. A mission like that could also fill in the missing pieces of the puzzle, expanding our understanding of worlds in the outer solar system. The future of exploration in the outer solar system is taking shape, with established space agencies and emerging space powers prioritizing missions to Uranus and its moons. In 2022, an orbital mission and probe to Uranus were included in NASA's priority list for the 2023 to 2032 Planetary Science Decadal Survey. This decision underscores the growing importance of studying the ice giants, which remain largely unexplored. The proposed spacecraft will focus on the plasma environment, radiation, structure, and evolution of the Uranian system. The mission, set to launch in February 2031 and reach Uranus by 2043, will provide critical insights into the dynamic processes governing ice giants. The spacecraft will have a dry mass of approximately 1 ton and, in addition to its primary objectives, will collect data on Uranus's atmosphere and rings. The launch window for this mission is open between 2030 and 2034. China is also entering the field with its Tianwen for mission targeting Jupiter and Uranus, scheduled for launch in 2030. Tianwen will carry 2 spacecraft on a long March 5th rocket. One probe will head to Jupiter's moon Callisto, while the other will fly by Uranus. This ambitious mission will mark China's first exploration of the ice giants. The spacecraft, though smaller in mass compared to NASA's mission, will also be equipped with instruments designed to study Uranus's magnetosphere and will venture into the outer solar system using a series of flybys to gain the necessary momentum. The achievements of the Voyager missions in exploring the outer planets have paved the way for future discoveries. But the path to a true understanding of space lies in our endless curiosity and exploration. As we continue to gaze at the stars, their legacy inspires us to embark on new ventures, providing the foundation upon which humanity builds its understanding of the universe. In the vast expanse of space, among countless stars and galaxies, there is a whisper, the whisper of a distant star that's traveled light years to reach us here on Earth. This is not a science fiction tale, but a reality of our universe, a testament to the continual growth of our understanding of the cosmos. Scientists, eavesdropping on space, have detected a signal, a radio wave from a star system not so different from our own. A star known as YZ Ceti is located just 12 light years away. But it's not just any signal. This signal carries a potential signature of a magnetic field very similar to the one that protects our own planet. A magnetic field that may envelop a rocky, Earth-sized exoplanet orbiting YZ Ceti. What could it mean? Could this distant world be more like our own than we've ever imagined? And what could it tell us about the search for life beyond our solar system? Let's go light years across to delve into the mysteries of radio signals in space and explore the magnetic fields of distant worlds. In the boundless silence of space, radio signals can, without guile, be called whispers. But what are these signals, and how do they propagate over such vast distances? In space, radio signals are a type of electromagnetic radiation, just like light, X-rays, or microwaves. They're generated by a variety of sources, from stars and galaxies to artificial satellites and spacecraft. These signals travel at the speed of light, carrying information across vast distances in space. They can tell us about the composition of stars, the presence of planets, and even the origin of the universe itself. But how do we detect these signals? The answer lies in the technology of radio astronomy. Radio telescopes, such as the Very Large Array in New Mexico or the now-defunct Arecibo Observatory in Puerto Rico, are designed to detect and analyze radio signals from space. They are our ears to the cosmos, listening to the faint whispers of the universe. Once a signal is detected by a radio observatory, it is analyzed using sophisticated algorithms and computer models. These analyses can provide extensive information about the source of the signal, from its location and distance to its physical properties. But radio signals from space are not just a scientific curiosity. They also have practical applications. For example, radio signals from satellites are used for GPS navigation, weather forecasting, and Earth observation. They are an integral part of our modern technological infrastructure. So, the next time you look up at the night sky, remember there's a whole symphony of signals playing out there, a cosmic conversation, an orchestra that we're just beginning to understand. Let us return to the constellation of Cetus, the sea monster, in which lies a star that whispers to us across light years. Her name is YZ Ceti. YZ Ceti is a red dwarf, smaller and cooler than our sun. It is located 12 light years away, a close neighbor on a cosmic scale. But what makes YZ Ceti truly fascinating is not the star itself, but what revolves around it. At least 3 exoplanets are known to orbit around YZ Ceti, the innermost of which, YZ Ceti b, is of particular interest. YZ Ceti b is a rocky, Earth-sized exoplanet that orbits very close to its parent star. In fact, it is so close that its year, the time it takes to make one revolution around YZ Ceti, is only 1.6 Earth days. Recently, using the Very Large Array, scientists at Bucknell University, Professor Jackie Villotson and her colleague J. Sebastian Pineda detected a repeating radio signal coming from YZ Ceti. The signal was recorded at a frequency of 2 to 4 gigahertz. It appears to be modulated by the rotation of the star and the orbit of YZ Ceti b, indicating an interaction between the star and the magnetic field of the planet. This discovery could have major implications for our understanding of exoplanets and their magnetic fields. Although YZ Ceti b is unlikely to be teeming with life due to its close proximity to its star, the detection of its magnetic field is important because it provides a method for discovering more life-friendly worlds in the future. But what does this signal really mean, and why are magnetic fields so important in our search for life? To answer these questions, we need to look deeper into the invisible force fields that shape our universe. Magnetic fields are a fundamental force of nature. They guide the hand of the compass, help birds navigate their long migrations, and protect our planet from the harsh solar wind. But magnetic fields are not just an earthly phenomenon. They also play an important role beyond the Earth. Our Sun, for example, has a complex and dynamic magnetic field. It controls the Sun's activity, from the formation of sunspots to the eruption of solar flares. Magnetic fields also shape the structure of galaxies, directing the movement of interstellar gas and influencing the formation of new stars. But perhaps the most intriguing role of magnetic fields in space is their potential impact on planetary habitability. A strong magnetic field can protect a planet from harmful radiation from its star, helping to maintain a stable atmosphere and perhaps even conditions suitable for life. That's why it's so interesting to detect a potential magnetic field on the exoplanet YZ Ceti b. This could provide valuable information about the planet's atmosphere and its potential to support life. How do magnetic fields affect the detection and interpretation of signals from space? To understand this, we need to delve a little deeper into the nature of radio signals and magnetic fields. Radio signals are a type of electromagnetic wave, which means they are composed of oscillating electric and magnetic fields. These fields can interact with other magnetic fields they encounter as they travel through space. When a radio signal passes through a magnetic field, it can be altered in various ways. Its direction can be changed, a phenomenon known as deflection. Its polarization, or the orientation of its electric field, can be rotated. Its frequency, in other words, the number of waves passing through a point in a given time, can be shifted. These changes can provide valuable information about the magnetic field that caused them. By studying these changes, scientists can infer properties of the magnetic field, such as its strength and orientation. But magnetic fields can also pose problems for detecting signals from space. They can cause interference, making it difficult to detect the signal. They can distort the signal, making it difficult to interpret. This is why the study of magnetic fields is so important in the field of radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop methods to correct these effects and extract valuable information hidden in signals from space. To better understand the influence of magnetic fields in creating favorable conditions for life on a planet, let's turn our gaze closer to home, to a familiar red-headed neighbor in our cosmic backyard, Mars. The red planet has long captured our imagination with its towering volcanoes, deep canyons, and hints of liquid water. It is one of the most intriguing places in our solar system. But Mars also presents us with a mystery. Unlike Earth, Mars has a very weak and inhomogeneous magnetic field. This has serious implications for the planet's atmosphere and its ability to support life. Mars's magnetic field is not created by a dynamo in its core like Earth's. Instead, it is the remnants of magnetism trapped in the planet's crust from the time when Mars actually had a global magnetic field. Without a strong magnetic field protecting it, Mars's atmosphere is directly exposed to the solar wind, a stream of charged particles emitted by the sun. Moreover, new models, presented by R. Sakata, the University of Tokyo, and others, suggest that a weak magnetic field, like Mars's after its dynamo turned off, could actually lead to a more rapid loss of atmosphere than if there were no magnetic field at all. Modeling has shown that a weak magnetic field results in the fastest rate of atmospheric ion loss, 6 times faster than without a magnetic field. The reason is that the weak magnetic field strength lines are easily repelled by the solar wind, creating a path for ions to escape into space over the night side of Mars. This suggests that Mars's remaining magnetic field may have hastened the planet's transformation into the cold and barren world it is today. Over billions of years, this caused Mars to lose much of its atmosphere, a process known as atmospheric stripping. This turned Mars from a potentially warm and wet world in its early history into the cold and dry planet we see today. The case of Mars provides a vivid illustration of the importance of magnetic fields to a planet's habitability. It shows us that without a strong magnetic field, a planet, even one as Earth-like as Mars, can lose the things that make it habitable: atmosphere and water. By the way, we've already looked at the problems and potential solutions to make Mars a second home for humanity in a separate video. Exoplanets, planets orbiting stars outside our solar system, have recently become a major focus of astronomical research. With more than 1,000 discovered to date, they offer a wealth of opportunities to learn about the diversity of planetary systems in our galaxy. One of the most exciting developments in this field was the discovery of the first known magnetic field on an exoplanet in late December 2021 by an international team of astronomers who used the Hubble Space Telescope for their research. It was discovered on a Neptune-sized planet called HAT P11b. HAT P11b is located about 123 light-years away in the constellation of Cygnus. It is a hot Neptune, a type of exoplanet that's similar in size to Neptune but much closer to its star, resulting in high temperatures on the planet's surface. The detection of a magnetic field on HAT P11b was a groundbreaking discovery. It showed that exoplanets can generate magnetic fields just like planets in our solar system. As we mentioned earlier, studying the magnetic fields of exoplanets can provide valuable information about their internal structure, atmospheric properties, and potential habitability. For example, a strong magnetic field can protect a planet's atmosphere from stellar winds, helping to preserve conditions that could support life. That brings us back to YZ Ceti, an exoplanet from which a signal was recently detected. If the signal is indeed indicative of a magnetic field, it could have major implications for our understanding of this exoplanet and its potential for life. Traveling through space, from the familiar landscapes of Mars to the far reaches of YZ Ceti, we've truly come to realize the invisible power of magnetic fields, the profound effects they have on planets, and their potential to harbor life. The field of studying signals from other galaxies has grown rapidly over the past few years. For example, the Giant Meter Wave Radio Telescope in India has detected a faint signal from the most distant galaxy to date. The signal detected by YZ Ceti opened another new window into the universe, reminding us how much we still have to learn about our world. As we look to the future, the study of signals from other galaxies will continue to be the focus of space research. So, when we look up at the night sky, let's remember that we're not just looking at stars and galaxies. We're looking at a universe filled with unseen forces, whispered signals, and hidden possibilities. And as we continue to listen and explore, who knows what we might discover next? In the vastness of our system lurks a considerable mystery, a source of energy and life: our sun. For a decade, the Space Guardian NASA's Solar Dynamics Observatory (SDO) has been our unblinking eye on this fiery giant. This mission, launched into space on February 11, 2010, set out on an odyssey, not just to observe but to unravel the mysteries of our nearest star. Imagine a world where a single second reveals a story millions of years old, where plumes of fire burst from the surface of the sun, larger than the Earth itself. It's a world that SDO explores, a world where every 3/4 of a second a new image is captured, each one a piece of the puzzle in understanding the sun's impact on our solar system. As we venture through a decade of solar observations, we're immersed in a realm where colossal waves ripple across the sun's surface, where plasma eruptions challenge our understanding of physics, and where the solar cycle resonates throughout the solar system. This is not just a journey of a satellite and a star. It is a story of discovery, the challenges faced, and overcoming them. Our journey with the Solar Dynamics Observatory begins with a momentous event. Its launch on February 11, 2010. Amidst the roar of the engines and the fiery takeoff of the Atlas V rocket, SDO began its mission to explore the mysteries of the Sun. This launch marked not only the beginning of the mission, but also the start of a new era in solar observations. Once in space, SDO moved into geostationary orbit, positioned to have an unobstructed view of the Sun. Its main goal: to understand the Sun's influence on Earth and the solar system by studying the solar atmosphere in unprecedented detail. Central to this mission is a suite of sophisticated instruments aboard SDO, each designed to study different aspects of the Sun's behavior. Prominent among them is the Atmospheric Imaging Assembly (IA). This remarkable instrument takes images of the solar atmosphere at different wavelengths, each revealing different features of the Sun. The capabilities of the AIA are truly revolutionary. It observes the Sun in 10 different wavelengths, each tuned to a specific temperature of solar material. This allows scientists to see the Sun's surface and atmosphere in a spectrum of colors, with each color revealing unique phenomena. AIA's observations have been instrumental in advancing our understanding of solar dynamics, from cooler and darker sunspots to blazing hot coronal loops. Over the past decade, it has tirelessly observed the Sun, taking more than 425 million high-resolution images. Each image contributes to a continuous stream of data, painting a vivid portrait of the Sun's dynamic behavior. Why do we study the Sun so diligently? The answer lies in the Sun's profound influence on our system. It is the heart of our cosmic environment, controlling processes from polar lights on Earth to weather patterns on other planets. Understanding the Sun means understanding the fundamental processes that govern our corner of the universe. Through the eyes of the AIA, we witness the story of the Sun unfold in real time. Ejections of solar material, twisting magnetic fields, and the intricate dance of solar flares have all been captured in stunning detail. The AIA didn't just open a window into the Sun's activity. It paved the way to understanding the complex interactions that drive solar weather. This decade-long observation has revealed the dynamic nature of the Sun in unprecedented detail. From the ebb and flow of solar flares to the mysterious 11-year solar cycle, SDO has provided insight into phenomena that were once mere speculation. The mission has witnessed previously unfathomable solar events. Across the vast expanse of space, the Solar Dynamics Observatory plays the role of a vigilant observer, capturing every nuance of the Sun with unprecedented precision. Over its decade-long operation, SDO has amassed a stunning collection of more than 425 million high-resolution images, creating a continuous image of the Sun's ever-changing face. Imagine a world in which every fraction of a second reveals a new aspect of our star. SDO operates in such a mode, acquiring images of the Sun every 75 seconds. This relentless pace of observation allows us to see the dynamic nature of the Sun in real time, capturing processes and changes that were once beyond our view. SDO's ability to observe the Sun at different wavelengths has opened up new possibilities for understanding our star. Each wavelength reveals a unique layer of the Sun's atmosphere, from its turbulent surface to the outer limits of its corona. This multi-wavelength approach allows us to see the Sun in all its manifestations. Among the wavelengths that SDO observes, one that stands out is the extreme ultraviolet wavelength of 17.1 nanometers. This particular wavelength gives us a unique view of the solar corona, the outermost part of its atmosphere. The corona is a hotbed of solar activity, where temperatures reach millions of degrees and where the mysteries of solar phenomena, such as coronal mass ejections and solar flares, lie. Through the SDO prism, the corona is no longer a dark region but a bright, dynamic environment. We see coronal loops, giant arcs of plasma driven by the Sun's magnetic field, and witness eruptions that send waves of solar material into space. These observations are not just visually stunning. They are key in helping us understand how the Sun affects space, weather, and, in turn, our own planet. As we continue to explore the sun with SDO, every image and observation at every wavelength adds to our understanding of our star's enigmatic corona, revealing a dynamic and complex celestial body like never before. By embarking on a quest to decipher the 11-year solar cycle, the Solar Dynamics Observatory has been at the forefront of solar science. This cycle, a rhythm that's puzzled astronomers for years, is characterized by periodic changes in the sun's activity, including the frequency of sunspots, solar flares, and coronal mass ejections. SDO's decade-long observations cover nearly a full solar cycle, offering a front-row view of the sun's changing dynamics. During periods of solar maximum, the sun is a swarm of activity, teeming with sunspots and solar flares. Conversely, during solar minimum, the sun enters a quieter phase with fewer sunspots and less surface activity. Throughout its mission, SDO has witnessed and meticulously recorded many solar events. Incredible eruptions of plasma, known as coronal mass ejections, have been captured in detail, revealing the enormous energy released as these events unfold. Solar flares, intense bursts of radiation, have been observed in different wavelength ranges, providing insight into the mechanisms that trigger these explosive events. In addition to the spectacle, SDO has also observed rare and mesmerizing passages of planets along the sun's surface. These events, while exciting in their own right, serve a more important purpose in solar science. They offer unique opportunities. If you put a cannon on a mountain and shoot a cannonball horizontally, it will fall vertically to the earth after flying a short distance. But if you shoot it with a very high force, for example, up to 4,500 miles per hour, the cannonball will always be in a state of free fall and will not reach the surface. According to Isaac Newton, this is the state in which our moon, and in particular all other planets, even outside the solar system, are located. This is how Newton came to the conclusion that gravity is a universal force for the entire universe, acting in the same way everywhere. Moreover, Newton's law did not contradict, but complemented other relevant laws. For example, the three laws developed by Johannes Kepler explain the movement of planets in outer space. The law of gravitation can be derived from each of Kepler's laws. Thus, according to Kepler's first and second laws, the orbit of each planet around a star is an ellipse, which means the distance of the planet to the star is constantly changing, including at the closest point from the planet to the Earth, perihelion, and the farthest point, aphelion, where the planet travels the same distance in the same time. Newton's law describes the acceleration of massive objects with respect to the distance to the star. In particular, the third law, which explains that an increase in the orbital radius affects the period of rotation, is also explained in the same way. Moreover, the force that keeps the planets in orbit is proportional to the product of the masses of the sun and the planet, and inversely proportional to the square of the distance between the two space bodies, just as it is between objects on Earth. However, Newton's law could not explain several important scientific observations. For example, Newton's theory explained the motion of the planets around the sun well, except for one, Mercury. You may remember that Mercury has a strange oval orbit, but that's not the strangest thing. Its closest point of convergence is always in different places and moves slowly around the sun. This process is called precession. Although this phenomenon is characteristic of all planetary orbits, it's most obvious and surprising in Mercury. The precession of Mercury's orbit is 5,600 angular seconds per 100 years when observed from Earth, but the actual precession time of the planet is 5,557 seconds. Now, those lost 43 seconds cannot be explained by Newton's theory. However, all of this and much more can be confirmed by another theory that is considered fundamental to modern science: Albert Einstein's general relativity. Almost 300 years after Newton's revolutionary discovery, Einstein introduced the world to his view of the concept of gravity in the general theory of relativity, GR. GR was preceded by the special theory, in which Einstein described that space and time should be perceived as an inseparable phenomenon, such as absolutely everything in the universe moves simultaneously in time and space. According to GR, He explained that massive objects are capable of curving time and thus affecting other objects around them, and this curvature is gravity. While Newton's theory was based on a falling apple, Einstein imagined a person in a falling elevator to explain his idea. As he falls, he doesn't feel his weight because both his body and the elevator are falling at the same speed. However, when the person is moving up in the elevator, he feels accelerated, and it seems that the floor is resting on him. However, if there are no windows in the elevator, then the person will not be able to tell what he or she is experiencing from his or her point of reference, falling in a gravitational field or moving at a constant speed in a small region of time. In Einstein's theory, this is called the principle of equivalence. In fact, if, according to Newton's law, a person falls down due to gravitational force, then, according to Einstein's theory, it's due to the absence of a force that pushed the person up. That is, a person is affected by the force generated by the elevator floor, but it is not gravity. This also implies that we are always in a state of acceleration unless we're in a state of free fall or inertial motion from our point of reference. So then, Einstein concluded that gravity and acceleration are one and the same, and therefore we're in a state of free fall until an obstacle appears in our path, which became the basis for understanding that gravity is not a force. This is a very unexpected statement. Let's take a closer look at the theory of relativity. So, as we've already noted, according to Einstein, gravity is a geometric curvature of a four-dimensional time-space. Its property is not a force acting in space. One can simplistically try to imagine time as a two-dimensional drawn fabric in which massive objects like the planet and sun create funnels. But this is not quite the right idea. A better option is to imagine time as a three-dimensional grid consisting of lines, geodesics, along which planets move in free fall. They are massive enough to distort the lines along which any objects move. That is why it may seem to us that, for example, cosmic bodies are attracted to each other. The theoretical physicist John Wheeler explained this idea quite simply. Space-time tells matter how to move, matter tells space-time how to curve. We can't see the curvature directly, but we can see the effect of Einstein's gravity. For example, if the crew on the ISS is flying right next to the Earth, they will move in a circle due to the curvature, although from their perspective it will seem they are moving straight. But a large object prevents them from moving in lines. Furthermore, we can observe this on Earth. If two people move from a considerable distance to the North Pole, they will meet as they approach it. No force would act on them. They would simply follow curved lines due to the sphericity of the Earth. The same is true for light. Newton assumed that light is also bent by the gravitational force of massive bodies, like all other objects. So the actual location of a light source, like a star, is different from what we see. However, modern science knows that light has no mass, so how could it be affected by large cosmic bodies? Einstein, in turn, expanded that light, like you and I, moves along the same lines of geodesy. Since, according to GR, the lines around heavy objects are deformed, light changes its course, meaning gravity does not act on the light itself. However, Einstein's calculations prove that the angle of light deflection was almost twice as large as according to Newton. Einstein's idea was confirmed by astronomers Arthur Eddington and Charles Davidson while observing a solar eclipse in 1919. They compared the actual location of the stars with the light captured in the photographs and were able to confirm that the angular deviation is indeed approximately 1.75 angular seconds, as calculated by Albert Einstein. In particular, GR can also answer the question about the strange orbit of Mercury since, according to its calculations, the planet's orbit is shifted by 43 angular seconds due to the curvature of space. In addition, another proof that gravity is a curvature of time is that a wave of light can lengthen and lose its intensity due to the influence of massive bodies. So, if an observer is in an accelerating spacecraft, then, in his eyes, the wave of light emitted from the bottom point would be elongated relative to its original wavelength. This, in turn, would cause the color of the light to change from red to blue. This phenomenon is called the redshift of light, and is not predicted by Newtonian gravity. In 2016, Professor Andrea Ghez led a team of researchers to observe the blue star SO2, which came close to the black hole Sagittarius A star. If Einstein's theory is correct, then the light wave from the star should have changed its color to red for the scientists' reference point, and the star did indeed glow red, which again confirmed Einstein's gravity. So, Einstein's gravity model has made a real breakthrough in understanding the physical processes taking place in our universe. At present, it is confirmed by perhaps not all tests of its reliability and reveals many details of time-space. Nevertheless, the Newtonian model can still be a serious competitor for GR. For example, while observing the rotation of disk galaxies in the 1930s, Danish astronomer Jan Oort first noticed that the rotation speed of stars on the edge of such galaxies remains constant, although they should be moving much slower. The solution to this paradox is the hypothetical dark matter, first described by astronomer Fritz Zwicky, which surrounds galaxies. According to current estimates, about 70% of the universe consists of dark energy, 27% dark matter, and 5% ordinary matter. However, although dark matter is an important hypothesis for explaining this phenomenon and many others, such as bullet clusters, its existence has not been precisely confirmed so far. On the other hand, a modified model of Newtonian gravity, modified Newton dynamics, proposed by astrophysicist Mordechai Milgrom, can explain the orbital rotation state. There are other rules for objects with much lower acceleration than in our system. Milgrom modified the formula of gravity by adding the constant a_0, which defines the critical point for acceleration. So, if the acceleration caused by gravity reaches this point, then Newton's laws, which were in effect before the critical moment, will be replaced by the new laws introduced by GR, and the inverse square law that we observe in our solar system would stop working, which will equalize the acceleration, meaning it will not depend on the distance from the center. This theory, in fact, explains the motion of stars and many other galaxies without the presence of dark matter. The universe, with its complex web of galaxies and cosmic structures, may have a form of consciousness. The idea of a conscious universe is still a subject of debate and research, yet it's firmly planted in the realm of speculation. Although it encourages us to think about our place in the cosmos and the interconnectedness of all things, the idea enters metaphysical territory and should, therefore, be treated with caution and critical thinking. Having considered speculative ideas of a conscious universe, we turn our attention to a more grounded and scientific theory, the fundamental theory of consciousness of Donald Goffman. Dr. Donald Goffman, a renowned neuroscientist and philosopher, has devoted his life to unraveling the mysteries of consciousness. His groundbreaking theory seeks to explain one of the most mysterious phenomena in existence, the nature of conscious awareness. Goffman's theory is built on the premise that consciousness is not simply a byproduct of complex computations in the brain. Instead, he argues that consciousness is a fundamental aspect of reality, akin to space and time. Drawing on quantum mechanics, neurobiology, and philosophy, Goffman's theory explores the interplay between micro and macro levels of existence. He suggests that consciousness arises from the complex interactions of quantum particles within the brain, governed by principles beyond traditional physics. Goffman's work has led to new experiments and collaborations across scientific disciplines. His theory has been tested through rigorous empirical research using advanced technology to explore the depths of consciousness. Although Goffman's theory has received the support and admiration of many in the scientific community, it has not been without controversy. Critics argue that the theory's reliance on quantum mechanics and its bold claims about the nature of reality require further confirmation and study. Nevertheless, Donald Goffman's fundamental theory of consciousness offers a new view of consciousness that bridges science and philosophy. The connections between the universe and neural networks go beyond mere scientific curiosity. They open the door to deep philosophical reflection and have broader implications for our understanding of existence. These connections invite us to see the universe not as a collection of isolated objects, but as an interconnected network of relationships. They inspire new ways of looking at technology, ethics, and our responsibility as inhabitants of the cosmos. The study of the universe and consciousness has been a central theme of philosophy for millennia. From ancient Greek thinkers to modern philosophers, the quest to understand reality, existence, and our place in the universe has shaped human thinking. Some see the universe as a deterministic machine, while others take a more mystical view. The connections between the universe and the mind only add a new dimension to this age-old debate. The idea of interconnectedness is not just a scientific observation. It is a call to reflection. It invites us to see ourselves as part of a greater whole, realizing the delicate balance of life in the universe. It forces us to think beyond ourselves and consider the impact of our actions on the wider cosmos. The journey ahead promises exciting discoveries. While the connections between the universe and neural networks are fascinating, it's important to approach them with scientific rigor. Misinterpretations and sensationalism can lead to misunderstandings and detract from the true scientific value of these discoveries. So, let our curiosity guide us in our exploration of the cosmos, and let our critical thinking help us stay grounded